All right, in the last video, we set up how to do component method and went over some basic trig that we're going to use here in that problem. That's where these four equations come from. Now, one of the things I didn't mention in that last video, which hopefully you're now watching this one, is these two equations, x going with cosine and y going with sine, does consistently work as long as angle is measured from the x-axis. Okay. If it's not measured from the x-axis, those do technically switch. So I think there's a problem or two on your homework where you'll have to make sure you have an angle from the x-axis, or technically those trig equations can't switch. But the reason why that works is if it's measured from the x-axis, then the x is always going to be the adjacent. Because you've heard me say on the regular, whenever we draw our triangles, we always draw them from the x-axis. So you can see that there's the angle, there's the angle. The x is, in fact, always adjacent. So what I'm going to show you now is, like I said, the component method. Now, I've got a visual representation. I kind of redrew this, hopefully a little bit more of a clear way. And I did the graphical. You don't have to technically draw anything for this method. I drew a line in the middle here. Everything I put to the right of that line is actually what you need to do to solve this particular problem. You don't need to do anything here. Now, what I would suggest you do for the sake of your homework and problems on tests in component method is sketch. Just real quickly sketch where it should go so you have a good idea of what your answer should be, so you know if your math is specifically screwing up. But what did we say we wanted to do with components? Well, what we wanted to do is we wanted to add along the x and add along the y. So what we need to do is we need to take each vector, starting here with the first one, and figure out how far they go along the x and along the y. Again, I'm going to draw on the picture so you can visually see what I'm talking about, but you don't actually need to do this for your homework. So if I draw this x-axis right here, all right, and the, let's look it all, okay, and the y-axis right here, the question is, what are these two vectors of the first one? That's got to be 90 degrees if it's x and y, okay? What are those two vectors that make up this 240 at 25 degrees? So let's call this x1 and y1. Okay? Well, how do we get with a magnitude and an angle? x1 and y1, boom. Just these two equations already tell us that, magnitude and angle. So x1 is going to be 240 newtons times the cosine of 25 degrees, because 250 is my magnitude and 25 is my angle. And to get the y, I literally do almost the exact same thing, except instead I put sine of 25 degrees. Let's go ahead and calculate that real quick. Okay, the first one here should be 217.5. And the second one, I'm going to talk about the units here in just a second, is, let's see, 101.4. Now, one very important thing that seems like a small thing, but is a giant thing long term, is the labeling of these. One, I do want to keep a label of newtons on this, because if I write a number, I write its units. You can see that on pretty much every single number that I put up here. The other thing that's really important is putting this thing that is called an x hat, because it's in the x direction. That is a quick shorthand for you that will take you less than a second and save you so many times. Okay, so I require it, just straight up require it. And that is to say, this is its direction. It's going 217.5 newtons in the x direction. And so for here, 101.4 newtons, this will be y hat, meaning it's going 101.4 newtons in the y direction. Just a quick way of showing direction, as opposed to needing an angle to do it. X and y hat technically tell us our angle. X hat tells us at 0 degrees and y hat tells us at 90 degrees. All right, so I know how far this goes along the x and how far this goes along the y. So for my number line here, 0, 1, 2, I've done this one. I know how far it goes along the x and how far it goes along the y. So now what do we need to do? We need to figure out the next one. All right, so how do we do that? Well, we just go to the very next vector, okay, this one right up here, and we split it up into its x and its y. Now when I draw a picture, notice that I draw it from up here, from the origin. How much of it's x? How much is its y? That x was not quite perfect. That's all right. We'll call that x2 and y2. So how do I get x2? Exactly the same way as before. Magnitude's 140. Cosine, because the angle is measured from the x, and this angle is 70 degrees. And y2 is almost the same. Sine of 70 degrees. So punch that in, and I get 47.9 newtons x hat and 131.6 newtons y hat. So now I've got how much these are. So what do I need to do to figure out how far it goes along the x and the y? Well, you simply do what it does here. You add them. Now let me show you visually, technically, what's going on. Ultimately, we want to know what r is. We want to know what is the answer to that particular vector. So what we need is we need to know how far it travels along the x, how far it travels along the y. We'll call this x total and this y total. Hopefully you can see pretty clearly visually that x total is simply x1, which goes from here to here, plus x2. So x total is x1 plus x2, which is equal to 217.5 newtons x hat plus 47.9 newtons x hat. And then we'll do the same thing for the y. Add y1, right? y1 plus y2 to get the y total. y1 plus y2. You don't have to show these particular equations. It's not the worst idea in the world, but let's go 101.4 newtons y hat plus 131.6 newtons y hat. Add those both up in the calculator and you end up with 265.4 newtons x hat and 233.0 newtons y hat. All right, so what do we do now? Well, technically, we're done, okay? Technically, okay? This is an answer. That's just the answer in component method. It tells us how far it goes along the x and how far it goes along the y. How far it goes along the x, arrow. How far it goes along the y, arrow. That is the answer to that, just in another method. In the exact same way that these two added together are the exact same thing as 240 newtons at 25 degrees. They mean the exact same thing. Now, what we are going to do is we're going to put another step on the end of this simply so that we get the answers that are the exact same as our answer key. They're in what's called polar form, okay? Meaning we know its magnitude and we know its angle. But that is technically the right answer. There are going to be a lot of homework problems where I don't specify what I'm looking for. If I don't specify, then that is fine. That is an ultimate answer. But we are going to, for the sake of our homework right now, convert back to polar. Meaning, I keep saying polar, what is that? That's the whole magnitude and angle thing that we've been starting. How do I get this r? Well, remember that trig from earlier. We literally just take the total x and the total y, the total x and the total y, and do Pythagorean theorem. So I need r is equal to x total squared plus y total squared square root. X total is 265.4 newtons x hat. That needs to be squared. Plus 233.0 newtons y hat squared, square root the whole thing. And my magnitude ends up as 53.2 newtons. Make sure I said that right. 253.2 is correct. And to get the angle, I would just do inverse tangent. So the angle is equal to the inverse tangent of, let's see if that's still on camera right there. Barely. Okay? But I'm just going to, well, let's move it over slightly. Inverse tangent of the y. It is important to put the y on top, which is why these kind of exponents can be helpful as well, but 233.0 newtons y hat over 265.4 newtons x hat. Plug that in and you get 41 point, I'm just remembering from earlier, 3 degrees. So what is my answer? My answer is 353.2 newtons at 41.3 degrees. But as I said earlier, technically these are completely equal to each other. Okay? So if there is a homework or a test that I don't specify that I want it in that magnitude and angle, you could leave it exactly like this, and that would be completely fine as well. All right, that's how you do component method. This gets you to the final result of that arrow and doesn't take any drawings whatsoever. Although, reminder, I did say that I would highly suggest a sketch at the beginning, because what we're going to find out as we're working through these is there are some negative magnitudes, and that can kind of be tricky if you don't kind of know where everything should end up. You know, one thing you will notice in this is that because there's only 2 vectors, it creates a triangle. A lot of people notice that just the original by itself creates a triangle. Okay, that triangle is not particularly important. If there was a third vector, like let's say one that goes this way, you'll notice it no longer makes a triangle at all. It can make a weird shape. The triangle that we're caring about is taking an individual vector, finding its y, and its x. You'll notice the x is always drawn first. Okay, so x and y, and if I were to add a third vector, all you would do is split the third vector. You'd get x3 and y3, or fourth vector x4 and y4, and then at the end you just add all of the components again. That would get you your final in what's known as component or Cartesian coordinates, and you could convert to polar if required, but that's how you do the component method of vector addition.